In this tutorial, we're going to talk about a very important algorithm that demonstrates that not all forms of cellular automata have to be restricted to grids. In previous visualizations of this cellular automata that includes Conway's Game of Life and Langton's End, we identified the number of neighbors that a tile had, and based on the number of neighbors that share a particular state, we made a decision on the changes on the state of a particular tile. However, in this case, we'll use a system that connects two elements based on distance. For the first time, we'll introduce the use of angles, and these angles are going to help us identify the direction in which a particle has to move relative to the forces applied to it based on the proximity of other particles of the same or different types. We need to talk about Jeffrey Ventrella. Jeffrey Ventrella is a computer scientist and also a procedural artist that has been working with the concept of emergence for a while. You can also see in his webpage different patterns that arise when certain arrangement of particles and rules are applied into this free movement system. Today, we will implement this algorithm. Suppose that we start with a green particle. This particle lives in a two-dimensional world that is delimited by an x-axis and a y-axis. Next to it, there is another red particle that appears in the map. The green particle can have a positive association or a negative association towards that second particle, depending on their color. One of the most important elements we need to calculate is the distance between the particles, which will determine the force at which the green particle moves towards or away from this red particle. To calculate this value, we need to take advantage of the Pythagorean distance. We take the distance in the x-axis between these two particles and the distance in the y-axis between the two particles. Remember that because this is a two-dimensional system, our particles have to live in a coordinate x and y. For the green particles, we'll simply call these x suffix g and y suffix g. And the same goes for the red particle. To calculate the hypotenuse, which is the distance between the two particles, we need to take the square root of the opposite side of this green particle and the adjacent side of this green particle towards the red particle in the y and the x-axis respectively. Although the nomenclature here takes its names from the identity of the angle that is being defined here, that we could call theta, we would also just call them A and B. However, because in future tutorials we'll use these names, it's better if we stick to the nomenclature as soon as possible. We take the formula a square root of a squared plus o squared, and that's going to be equal to the hypotenuse h. This value h will later be connected to a matrix that tells us the association between different types of particles. From here we can see this matrix is symmetrical. The number of rows and the order of those rows matches the number of columns and the order of those columns, in such a way that we can summarize the relationship between two different red particles, two different green particles, and the association of green towards red and red towards green. From here, we can see that the green particle has a negative association towards the red particle. That means that the green particle will try to move away at the same orientation in which it is looking at the red particle, but in the opposite direction. How is this association connected with the distance h? We will use a piecewise function that is defined by 4 domains. The threshold between domains is defined by constants. The x-axis represents the distance h, and the y-axis represents the force, which can be positive or negative. In the first domain, we see what we called the personal space of the green particle. No matter how strong or positive the association between two particles is, At some point, these two particles are too close from each other and they have to get apart. This line is defined by the 2 points 0, -1 and rmin, 0, being rmin and -1 values that we can choose. There are hyperparameters in our algorithm. From rmin to rmith, we will have the forces of attraction or repulsion between the two particles when the distance h falls within this subdomain. The height of this line is entirely determined by the coefficient. If the coefficient is positive, we will have an attraction. Otherwise, we will have a repulsion. The third subdomain represents the distance at which the effects of the coefficient start to diminish. And finally, in this fourth subdomain, we have no effect. These could be considered the boundaries in the field of view of our green particle. So, where do we get this coefficient? The matrix of coefficients allows us to identify not only the sign, but also the magnitude at which these particles interact with each other. Because the sign is negative, we have a negative coefficient that is below the horizontal line of our plane. In this case, the distance between a green particle and a red particle will always have a negative association, except when the red particle is close to the point rmin and rmax. In a positive association, where the coefficient is positive, the bigger the magnitude of this coefficient, the steeper the curve is gonna get, which means that any distance between these two particles located in this subdomain or this subdomain will probably have very strong positive effects that will eventually make the green particle move towards the red particle. The bigger the coefficient, the stronger the force. Let's implement this using Python and Pygame.